Okay, Newton's 3 laws of motion, cut all dotted lines. Okay, so Newton was brilliant scientist, physicist and mathematician. We can thank him for calculus and pretty much all of our knowledge and understanding of how the planets move and how pretty much anything moves. And it all comes down to these 3 laws that he discovered, I suppose. Before him, there was a lot of confusion about why things moved and when they moved and what was going on. But the cool thing is he kind of figured it all out. All right, so first law, go and take this large piece of paper and glue it in. Glue in that large piece of paper. Okay, the first law is called inertia. Okay, the law states that an object at rest stays at rest, and an object in motion stays in motion at a constant velocity until an unbalanced force is applied. Now, that unbalanced force, okay, a force is any sort of a push or a pull, all right? When the forces become unbalanced, then it will do something different, all right? So, a few key words here for highlighting with your colors, okay? I recommend like 2 colors for this one. All right, so at rest or constant velocity. Okay, an object will either be at rest or have a constant velocity unless force is applied. Now, that's the law of inertia. The word inertia is actually from the Greek language, and the translation means lazy. What Einstein was saying is that Newton was saying all things are lazy. They just want to keep doing whatever it is they're doing, okay? So my pen, just sitting there, it's at rest. If it started to just move, we'd all get a little freaked out, right? Because we know something's got to make it move. There has to be some sort of force. So this would kind of make sense. This logically kind of falls in place. Okay? The constant velocity one, I'll have to convince you that in a moment. Okay? Now, inertia as a characteristic. Okay? How much inertia an object has. So, does the object have lots of inertia or a little bit of inertia? Depends on how much mass it has. So, my large inertia object, like a pair of scissors, relative to a pencil, okay? This has more inertia than this. This is lazier. All that means is it takes more force to get this to move than it does to get this to move. I apply the same amount of force on both of those objects. The scissors might not even move, but the pencil does. Okay? So this is lazier because it takes more force to get it moving. Similar, it takes more force to get it to stop if it's already moving. Okay? So the more mass an object has, the more inertia it has, the lazier it is. My favorite example with that one is when I was pregnant, okay? When I was pregnant, I was much more massive. And with all of that extra mass, I did a lot less moving. I literally never got out of my chair in my classroom. I swear, I rolled around in this thing everywhere, okay? So the more mass it is, the more mass it has, the lazier it is. Okay, so let's break it down a little bit into those objects at rest and those objects with constant velocity. So the objects at rest want to stay at rest. The unbalanced force that's applied will get them to move. It will start them moving, okay? So scissors at rest, if I apply an unbalanced force, it's enough force it'll start to move, okay? When something goes from rest and then starts to move, it accelerates. So we have an acceleration. A really interesting example of objects that don't want to move, and this example of inertia, is when you have the tablecloth pulled out from underneath the dishes and the dishes stay on the table. Have you ever seen that trick before? Oh, yeah. It's pretty fun. All right. It works when you have very little friction. So most plates have like rough bottoms on them so they don't slide around on the table as you're eating your food. Okay? You'd have to find plates with really smooth bottoms on them. You'd also have to do like a silk tablecloth. And you have to make it move really fast. And you can make it work. Not easy, but doable. So that's your objects at rest. They want to stay at rest. Objects in motion want to stay in motion, and they move at a constant velocity. Okay? This is something we have a really hard time visualizing here on Earth. Because if I, for example, I kick a soccer ball, goes flying across the field, right? Eventually it's going to slow down and come to a stop. Every single life experience you've had is something that's moving will eventually slow down and stop. Am I correct? Okay? So this law makes absolutely no sense to us. But if you consider doing it in outer space, get far away from any planets, go out there and kick a soccer ball. Okay? There's no forces acting on it. So it gets moving, your foot kicking it gets it moving, and once it's moving, it just keeps going and going and going. It's not going to change direction. It's not going to speed up. It's not going to slow down. There's nothing to make it change what it's doing. Okay? That constant velocity happens when there's no forces acting on it, or when all the forces are balanced, which I'll explain in the next journal entry. Okay? So the example of throwing a baseball in outer space, no friction, keeps moving the same direction with the same speed forever, unless a new force acts on it, like, you know, like the gravity from a planet or something like that. Okay? The unbalanced force. When the unbalanced force is applied, whatever that force is, it either speeds the object up, it either slows it down, or it changes its direction. Okay? So in the case of a soccer ball, me kicking it would speed it up. Okay? But if I'm like catching a baseball, I'm slowing it down. So it's either accelerating or decelerating, or changing direction, which we just learned that rotational circular motion, if you change direction of something, you accelerate it. Okay? So if I change direction, so if I have a baseball flying through outer space in a perfectly straight line, and I just tap it a little bit, apply a small force, it'll change its direction. And it'll now go in that new direction in a straight line. Make sense? Okay. So that is inertia, the first law. The second law is actually a formula. The second law is simply the formula F equals ma. Now, I would wait to glue it in just because we're going to write on it and then we can glue it in. Okay? So F equals ma. What do you think? Okay, back up. What does the M stand for, class? You should know this. Mass. What does the A stand for, class? Acceleration. The F is force. All right, units of measure. What are the units of measure for acceleration? Meters per second squared. Don't forget the squared. What are my units of measure for mass? Mass? Kilograms. Now, force. Okay? Technically, force is kilograms multiplied by meters per second squared. Kilograms dot meters per second squared. That's technically what it's supposed to be. But that's kind of a pain in the butt to say, and it's kind of a pain in the butt to write. The whole idea is to keep it short. So they went ahead and named it after Newton, and we call them newtons. Okay? So force measured in newtons, mass measured in kilograms, acceleration measured in meters per second. That is your formula. That is Newton's second law. The idea of this, the idea of application of this formula. You can go ahead and glue that in. Okay, so for the sake of a little bit of definition, okay, the picture here. What is going on in this picture? All right. We have two actions going on over here. We have somebody pulling and we have somebody pushing. Okay? I like this picture because it is the perfect example of the definition of force. The definition of force. A push or a pull. A pull or a push. That is your definition of force. Super simple definition. Go ahead and glue that in. This barely is going to fit. Okay. So, the force applied to an object with a specific mass will determine the acceleration of the object. That is Newton's second law in words. Okay? For most people, that just kind of sounds like blah, 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 blah. The acceleration of the object is proportional to the force acting on it. What does that mean? All right, well, let's write in here a little a below acceleration, a little uppercase F next to force. Okay? So the force and the acceleration. What this is saying, proportional. Force. As I increase the force acting on an object, how is that going to affect the acceleration of the object? It also increases. It's kind of like, okay, I'm driving my car. If I push harder on the gas, it will accelerate faster. Make sense? All right. What if we decrease the force acting on an object? What will happen to the acceleration of the object? It will also decrease. So as one increases, the other increases. As one decreases, the other decreases. We call that a proportional relationship. Force and acceleration are proportional. Now, the acceleration of an object is inversely proportional to its mass. Okay? So again, put a little a here for acceleration and a little m here for mass. Okay? So, if I have the mass of an object, okay, specific amount of force being applied, what happens if I increase the mass of the object? What's going to happen to the acceleration of the object? It decreases. It will still accelerate, it'll just accelerate much slower. Okay? My favorite example of that one, living here in Laredo, are the semi-trucks. Okay? They can go really fast. They can go 90 miles an hour if they need to on the interstate, right? But what's the worst thing is getting stuck behind them at a stoplight. Because they have such a huge mass, their acceleration is ridiculously slow. Like my great-grandmother, I swear when she drove, she accelerated faster than that. I mean, seriously. Okay? It's not their fault, it's just because they have a really big mass. So similarly, what if you decrease the mass? Okay? So think about sports cars. Really fast cars. They're pretty small in size. We decrease the mass so that when they want to race at the stoplight and the light turns green, they can accelerate much faster than the other vehicles because they've got a smaller mass and a really big engine. Okay? Does that make sense? So the rate of acceleration is very fast because of the small mass. Okay? That's an inversely proportional relationship. Now, something that might One way to think about proportional and inversely proportional, those are things we'll describe frequently, okay? A proportional, using the word proportional. So my 5-year-old daughter, no, she's 6 now. My 6-year-old daughter is absolutely horrifically addicted to sugar. She loves anything sweet, okay? So I'll make brownies, okay? And I serve a brownie with some ice cream to everybody in the family, okay? My husband, who's a big guy, will get a big brownie with like 2 scoops of ice cream. And then my daughter, little tiny 6-year-old girl, super scrawny, skinny, gets a smaller brownie with a small scoop of ice cream. And she gets mad. Why does Dad get such a big piece? It's so much more than I do. I should get just as much as Dad does, right? And then I teach my daughter, sweetie, your serving, how much I give you, is proportional to your size. You are a tiny little girl, and Dad is a really big boy. So you're going to get a smaller size serving. She doesn't really like that answer, but that's an example of proportional. Her serving size is proportional to her size. Okay, the serving is proportional to the size of the person eating it. Inversely proportional. So inversely proportional, example of my bathroom scale and my relationship with my bathroom scale. Okay, so if I stand on the bathroom scale and that number has gone up, my self-esteem goes down. Okay, inversely proportional relationship. If I stand on the bathroom scale and that number has gone down, my self-esteem goes up. Okay, that's an example of an inversely proportional relationship. Okay, yes? All right. So, go ahead, glue that in. Glue it in kind of to the right there. I know it's hiding a little bit of notes. I'm not too worried about it, but if you want to, you can rewrite that over here. Units for acceleration, if it doesn't quite fit. Meters per second squared. We're going to do Newton's third law on the oops page. On the oops page. So don't turn the page. Just move right over there to the oops page. Okay? So at the top of the oops page, I'm going to go ahead and glue it in, the remaining paper. Just right there below the first line. Okay, this is Newton's third law. When one object exerts a force on another object, the second object exerts an equal and opposite force on the first object. Okay? That kind of sounds a little like a blah, blah, blah explanation as well. Okay? And this one is actually, to be fully, completely honest, is kind of hard to believe at times. So it takes a little convincing. We have one object exerts a force. And we have a second object. A second object exerts a force. Okay? But the interesting thing about these forces is the equal and opposite. Equal and opposite. Okay, equal and opposite kind of sound a little like juxtaposed. Okay? So equal forces. Both of these forces have the same magnitude. Remember we talked about magnitude? When we're talking about forces, magnitude is about the strength of the force. Okay, so go ahead and write strength over here. How strong that force is the magnitude of the force. But they're going in they're opposite forces. Specifically, the thing that's opposite are opposite directions. Two objects. These two objects are pushing against each other. The force applied by object A has a strength of 10 newtons. That will guarantee for me that the force that object B is also exerting a force of 10 newtons. That's what we're talking about when we say same strength. They're both 10 newtons of force. But they're going opposite directions. A is pushing to the left, B is pushing to the right. Sorry, vice versa. A is pushing to the right, B is pushing to the left. Okay? Does that make sense? Opposite direction, same strength, equal yet opposite forces. All right. Again, this one's kind of hard to believe. Be fully honest. Let's go ahead and glue it in. Just a very little bit amount of glue. Just very little glue because we're going to write on that. Just enough so it sticks. If you put less glue, it'll dry faster too. Okay? Our two ladies there. Look at them very carefully. Careful observations. What's a little bit different about these two ladies besides the fact they're like pushing against each other? Ah, look at their shoes. What do we see with those shoes? We have ice skates. Okay? So the reason why we do this example on ice skates is because we're trying to go for like minimal friction. Like almost zero friction. Put them on skates and they push off against each other, and what happens? They actually move away from each other. We can see what those forces do to those two as they push away from each other. Okay? Yes? So let's take a close look at this. This is actually Newton's second law and Newton's third law simultaneously. They're pushing off from each other. Newton's third law says it doesn't matter how strong she is, and it doesn't matter how strong she is. If you look at her arms right there, buff lady. This lady, little old lady, skinny arms. Okay, yes? They push off from each other, and guess what? We're dealing with same strength forces. Okay? They're going to push off with the same force. So, she pushes, those forces are going to be the same strength. They're just going to be going in opposite directions. Okay? Same strength, opposite directions. But if you take a careful look at her body build and you take a careful look at her build, what can you probably tell me about the mass of the lady on the left compared to the lady on the right?
She's smart.
Lady on the left, she's packing a few more pounds. Lady on the right, nice and trim. So notice I drew that as a big M, that's a little m. Both lowercase, that one just bigger. She's got a bigger mass. She's got a smaller mass. Okay? Yes? So, the forces are the same strength. Large mass, small mass. What can you tell me about their accelerations? How is the big lady going to accelerate compared to the little lady? No, different mass, same force. Okay? So, let's say this is a 20 Newton force, this is a 20 Newton force. Okay? Those forces are the same strength. They push off from each other. That force, she gets 20 newtons of force, she has a larger mass, her acceleration is going to be small. She's got a smaller mass, her acceleration is going to be large. Does that make sense? Da, 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 da. Next example is our astronaut. So I'm a real nerd and I like science nerd movies, and one of the best science nerd movies that's come out recently is the movie Gravity. And in that movie, George Clooney has his jetpack on, it's run out of fuel, and he's floating away from the space station, and he just keeps floating forever because of inertia. Object in motion stays in motion with a constant velocity. There's no forces acting on him. He just keeps going forever, floating away, and dies. And I'm watching the movie. He lets go of Sandra Bullock's hand. And I'm like, okay, save yourself.
Oh yeah, she starts like
Save yourself.
floating.
Save yourself. And he doesn't. He could have saved himself. And I'm like, what the heck? Come on. Because he could have saved himself. And he knows Newton's, if he's an astronaut, dude, Newton's laws are like ABCs to him. Okay? Super simple. He knows he can do this and he knows how to do it. Why he doesn't do it? I guess just for film fun. I don't know. So, he has that backpack on, right? That jetpack is actually extremely heavy. Doesn't really matter if you're floating in space, but it's an extremely like large, heavy sort of thing. Okay? All he has to do is remove the backpack. Once he's removed the backpack, he and the backpack are now two separate objects. And all he has to do is push the backpack, throw the backpack, however you want to do it, push off from the backpack. Whatever force with which he pushes the backpack will push against him. And then he will start floating the direction he wants to go, aka back to the space station. Okay? So, okay, well, let's put it on like this. George Clooney versus backpack. Here's his backpack. Not really a backpack. His jetpack. Whatever. I can't draw that, so we're just calling it a rectangle. Okay? He pushes against his pack is going to push against him. So if he pushes with all the force he can possibly push against, all right, he'll push him. Instead of him moving this way, it'll now move him that way, the direction he wants to go. Because he pushes against that, he's going to move him that. It's going to push him that way. He's going to move that way. Does that kind of make sense? I'm sitting in my rolly chair trying to minimize friction, okay? And here I have the bench. Now, I know that if I push, for example, the crate, this direction, what direction does the crate move? The same direction I'm pushing, right? Objects move in the direction of the force applied. Yes? Okay. It'd be really weird if I pushed it this way and it went up, right? We'd be like, what's going on? Okay? We know that if you push that direction, that's really the direction object moves, right? Now, I'm going to push against my bench. Now, we all kind of know that the bench probably isn't going to move, right? But what happens to me? I moved backwards, right? So, if I moved this way, something must have pushed me that way, right? A force must have been applied to me in the direction opposite the direction I'm pushing in order for me to move that way. I push against the bench pushes against me. Am I convincing you? Okay? I give a little push. It gives me a little push. I give it a big push. It gives me a big push. Yes? Newton's third law. It doesn't matter even if the desk is, okay, the bench isn't thinking, I must push against her with the same force. It doesn't think, it doesn't do it, it just happens. It just happens, it's just how it works. Okay? Make sense?